Hey everybody, just like to welcome you all back to our YouTube channel. This is episode 2 of 6 in our Precast Concrete lifting course. So firstly, thank you for watching the first one. I hope you enjoyed it. I'll add a link on the screen to the first episode just in case you haven't seen it. So we'll start this one as we did the last with just some clips of some precast. So here, these are footage from JP Concrete, job in the UK, some transformer bases that we did a lift and design from Steve. Steve was very good to send us on these couple of videos. So here you see the crane being set up. The hole is dug. The truck is reversing back. It's a 20-ton transformer, 22-ton transformer. And we use wavy tail lifters here. So the walls were thin, maybe 200 mil thick. We needed to engage the rebar in and around the lifters. So we used wavy tails. So here's the second one just going in, more of the same. Yep, there we go. Okay, so we have some photos coming up of a bridge we done in Offaly. It's an end portal structure on some precast foundations. So you can see here it was an old masonry arch bridge was there, it had to be demolished, road closure, needed something quick. The precast end portals are a very easy structure to design and get in there quick. Foundations went in, 6 foundations, 7 portals, and they were all installed within a couple of days. Banner Precast Concrete made the units. You can see them coming in. So the foundation cells were 11.5 ton. The end portals using pin lifters were 13.5 tons, so 2 per load. Here you'll just see a little bit of a safety demo. One of the guys here is just cleaning out in and around the lifting pin. He's bringing the clutch down. He's going to pop it into place and lock it, that it's ready to go. Okay, so I'm going to let you over to Matt now, and he's going to give us the lecture 2.
So this is the next module in the precast lifting course. The last module we looked at determining the lifting demands, and now we're going to start looking at determining the lifting capacities, and particularly in this module we're going to focus on the tension failure modes. So essentially the lifters are going to experience both shear and tension depending on the angle of lift, and this module will focus on the tension failure modes. So looking at the course outline, as I said, we're moving on to lifting capacities now, and that's split across 2 lectures because there's quite a bit in it, and it can be equation heavy, but the intent is not to necessarily focus on the equations, more focus on what the equations mean, with diagrams, what they represent, what you need to look out for, etc. When you need to use equations, when you don't need to use some of them. And we'll have time at the end for questions on this. There's going to be no worked example in this lecture because it will continue into next week's lecture, and we'll have a worked example then that will comprise both content of these 2 lectures. It'll be the same worked example that we looked at for the demands last week, so you'll be able to follow the worked example right through the demand capacity approach. So module 2, again, we're going to give a quick recap of what we discussed last week. We'll just give a quick recap of how the pin lifters actually work, how the forces get transferred, flow of forces, and the clutch, etc. But mainly this is all about tension failure modes. And before we start, I'm going to have a quick recap of what we did last week. And one of the things that was brought to my attention, and we've had an amendment from last week's lecture, when we put up this slide last week on the types of lifting castings, we had a fixing socket in there by mistake there in the top right. So it's not recommended that these components are used for lifting. All the other components would remain valid. This particular component is generally used for fixing, so fixing steel brackets, etc., onto precast. And that's the main reason is primarily due to the fact that you've got a very small embedment and very little anchorage. You got other components here that look as if they have small embedment, but these ones have the possibility to add rebar back into the unit. And then obviously for flat slabs, you've got the flat plate, which only work when you have the additional rebar across the face of that flat plate. So they're all valid for lifting. This solid rod socket is not, so that's just an amendment from last week's lecture. In last week, I introduced you to the formula on the left here in red, and that's the general form of the equation required to determine the demands. So the demand is the action times partial load factor, and in the case of precast lifting, the action is the self-weight of the concrete. We're going to look at the right-hand formula now, which essentially has a similar format. The design resistance is the characteristic resistance divided by a partial factor, and that's going to be essentially expanded out a couple of different times for each of the different failure modes. So that's the general form of the equation. That's the one the Eurocode states, and it's pretty straightforward that your capacity is the calculated capacity divided by some factor of safety. For determining demands, we have the general form of the equation. As said, the design demand is equal to the characteristic demand times the partial load factor. The partial load factor, we said, can be taken as 1.2 because of some degree of certainty that we have over the unit weight of the concrete. We then spoke about two different situations where we need to calculate the demand at the demolding stage and the demand for lifting. The demolding is based on the adhesion to the formwork, and the demand for lifting is based on the dynamic behavior. So we spoke about that dynamic lifting factor where we can get 4 times the demand depending on the type of terrain and lifting machinery that we're using. So to get to the final demand then, we take the maximum of those two formulas and we apply the 4 influencing factors that need to be considered. Again, type of formwork, direct lifting coefficient, the number of effective lifters, and the angle of chains. And when we've all that done, we're able to break down the demand into a tension force and a shear force on the lifter. We then can take those in once we work out our capacities in this module and compare them. So this module, as I said, is the derivation or the calculation of the tension capacity of a lifter. Focusing on a lifting pin, and again, this is the same slide that we would have had last week. So in terms of the lifting pins, the majority of these lifters have the forged foot that gets cast into the concrete. The foot is the primary load transfer mechanism for the tension forces, and for the shear forces, there's generally direct contact between the clutch and the concrete. But we still, the shear force still would always look at the cross section of the shaft in terms of the steel checks. So the concrete dome former needs to be correct for the type of lifting pin, and we saw a similar load transfer mechanism last week for the wavy tail sockets, so I just don't have that slide here. So the failure modes for both the lifting pins and the wavy tail sockets are similar, and this is actually kind of raised in the Q&A last week as well. So we talked through that in a bit detail last week. So moving on to the capacity. So we have the general formula for the lifted capacity, and it starts out similar to what we saw for the demand. The design resistance is equal to the characteristic resistance times partial material factor lambda m, divided by the partial material factor. So for lifting design, we're dealing with 2 different materials. We have a steel component upon which the lifter itself is made, and then we have the concrete that surrounds the lifter to hold it in place. So we have to ensure that both the steel and the concrete are capable of resisting the demand that we would have determined. So we've got this table here, which comes from CEN 15728 to explain the partial factors that are required when you're calculating the capacity. So it presented here for the steel components, for reinforcing steel, pre-stretching strand, wire rope, and so depending on what kind of product you're using, it has a different partial factor. So the partial material factor here is a combination of the steel itself and this lifting and handling factor that is introduced when you're dealing with precast lifting. For the pin itself, so which is generally solid steel, you multiply the two factors together. So you have this top row here. So 1.25 times 1.8 will give you 2.25. So interestingly, if we multiply this by the partial load factor from last week, so in summary, we've got three partial factors that get applied when we're doing this design, some to the demand, some to the capacity. If you multiply all those together, the 1.25 here, the 1.8 and the 1.2 from last week, you end up with a value of 2.7. And that means that all the partial factors combined give a value of 2.7. And in the previous module, I mentioned that there was a difference between the way lifters were historically designed and the way they're designed in Eurocode. And lifters historically were tested and a global factor safety was applied between 2.5 to 3. So we can see some similarity then here between the old approach and the Eurocode approach, that you still end up with a similar factor of safety. So in terms of structures, or the solid steel component, the actual lifter, the global factor of safety would be equivalent to 2.7 when you work it out. Likewise, we have a similar partial material factor for the concrete, and you come up with similar alignments with the historical approaches. So again, concrete, we've got the gamma C, which is 1.5, and our lifting and handling coefficient, which is also given as 1.5. So 1.5 times 1.5 would be 2.25, and again times 1.2 will give you the factor of safety up at 2.7. So in terms of equivalency, the global factor of safety according to the Eurocode would be 2.7 for both the steel and the concrete components. So that kind of covers the partial factor aspect. Now we need to look at the actual characteristic capacity. So in order to do that, we need to understand how the unit can fail in tension. So there are a number of different ways in which the I suppose failure can occur. And it's common practice to classify any failure in terms of lifting design as either a tensile failure or a shear failure, or a combination of both, as practically all handling will include situations where the chains are angled. And when you do have a combination, there's a few little more things that you need to account for in terms of that interaction, and that will be covered next week. So here we have the 5 most common tension failure modes. The first failure mode is the steel failure of the lifting pin, and the remaining 4 are all concrete failure modes. Bond failure is the second one here. It's most associated with cast-in straight rebar, such as couplers, etc. So we kind of touched on that last week. And as mentioned last week, the shape of the wavy tail lifting socket is such that the bond failure is generally not an issue, and it's more the concrete cone failure that governs, which is this next one. And this is the most common and generally governs the majority of the time, but you still have to check them all. And as the name suggests, you can be seeing that it gets its name from the kind of shape of the failure mode. So this kind of wedge of concrete, this cone of concrete, breaks out. All the forces are concentrated down at the foot and all the pressure, and then it kind of forms a crack line. And we have some more diagrams that go into that in a little bit later. Then we have blowout failure, which comes to the fore when you have long lifters in narrow panels, where the concrete stress is too large at the foot and there isn't basically enough concrete at the edge to resist that, and you have local pieces of concrete popping off. So that constitutes a failure. And then the final one is splitting failure. It's dependent on the type of unit. It can result in horizontal or vertical cracking. For a wall panel, such as the image here, the failure plane is horizontal through the pin foot. If you had a slab, it would be in a corner. It might more result in vertical cracking. All concrete failures can be prevented by adding reinforcement in the vicinity of the lifting insert, the exception being maybe bond failure. But the likes of concrete cone, blowout and splitting, you can add additional reinforcement to prevent those failure modes. And it all depends on the geometry, the vicinity of the lifter to the edge, and guidance is given on some typical examples in the code on how to add supplementary reinforcement. But we're going to cover some supplementary reinforcement examples in the next lecture also. Quick look at potential shear failure modes. We're not going to go into it in much depth in this lecture, only in this slide here. And again, there's a potential shear failure in the actual steel failure in shear in the head of the lifting pin or socket, where that kind of top surface will kind of shear off. With 3 concrete failure modes then to be considered. First one there, mark B, that's a pry-out failure, and that can be seen from the image here and from the calculations when we get into them. It's very similar to a concrete cone failure. It's almost like a one-sided concrete cone failure where the wedge kind of just pries off, as the name suggests. And when we get into the formulas, it's very similar to concrete cone. The next and probably one of the most common ones that governs is concrete edge failure. And there are a number of factors to be considered here in terms of edges, distance of edges, etc. In the likes of slabs for lifting, it's generally not going to govern too much because your pins are far enough into the concrete, and if it's a solid slab, there's kind of no edges to worry about. If you had like a manhole slab where there's quite a large opening in the center and the lifters are relatively close to that central opening, well, then you would have to consider edge distance failure, because more often than not, you're lifting at an angle, and therefore that angle will create shear forces towards that edge. And then the final, or some examples where shear edge, I suppose, also comes in is when you're tilting panels. So when you're trying to tilt the panel, particularly wall panels, they're narrow, and you are going to be quite close to the edge, and the initial force is applied to the lifter 100% in shear. So therefore, you generally always will have to add supplementary reinforcement to ensure that the shear edge failure is prevented when tilting. The final failure mode in shear then is local concrete crushing, whereby basically the shaft of the lifting pin bears against the concrete locally and crushes the concrete, and hence preventing any further shear transfer as the lifter will fail in bending. Not as common with lifting pins because the load is spread out that bit more, like here with the dome. But if you're lifting with sockets and there's significant shear, there's potential for a higher compression here. And obviously, when you're demolding, you're going to have a lower age concrete, so that has reduced strength. So we have it's a quick calculation to do. So it's a quick check on that to ensure that locally you're not going to crush the concrete. If that concrete does crush, as I said, the lifter will essentially bend. So it's not pure shear anymore. There's actually going to be a component of bending in it. Similarly, when we get to it as well next week, there's an eccentricity factor to be accounted for. But the majority of lifting devices are designed to minimize that eccentricity. Pry-out failure can be prevented with some additional steel or increasing the length of the insert to give you more of a contact or more of a failure cone. Edge failure can be prevented by adding reinforcement, which is actually straightforward enough to do, and it's easy enough to fit that reinforcement in line with the main reinforcement to avoid congestion. Tilting reinforcement can sometimes be a little bit more difficult due to potential clashes, etc. So I'm going to try and get into some of the numbers now. And again, from here on in, there's probably a lot of formulas going to be on the screen. That you kind of have to just kind of take away and look at yourself. But the idea of this lecture is to explain how to use the formulas when they shouldn't be used, and what are the components what information is required in order to use the formulas. So I'm going to step through the steel failure modes first and show the relationship between the traditional approach and the Eurocode approach. As shown in the previous slide, the design resistance is equal to the characteristic resistance divided by the partial material factor. So, and on the previous table, a couple of slides ago, we showed that the partial material factor for steel solid sections, such as lifting pin, is 2.25. So it was 1.25 times 1.8 to give us that 2.25. So we can put that in up here. The characteristic tension resistance is calculated as the cross-sectional area times the characteristic ultimate tensile strength. So the characteristic shear resistance is calculated similarly as the tension, and you just divide by the square root of 3 for give you the shear. So the area of the shaft is known, it can be measured, it's always tabulated in brochures, and therefore the only unknown is the ultimate tensile strength. So any of the lifting suppliers should have test certs available for each product, and you're likely going to expect a value in around the range of 550 to 650 megapascals. So it's the ultimate tensile resistance, not the yield strength. It's the ultimate. And simpler to test it. It's just a simple tensile test to carry out those experiments. So what we can do is, if we take a 7.5 ton lifter, for example, so we'll crunch a quick number here, and according to the Eurocode, so a 7.5 ton lifting pin typically has a shaft diameter of 24 millimeters, and thus an area of 452 millimeters squared. If we take the lower bound for the ultimate tensile strength of 550, we can work down through the formulas and get a design tension capacity of 111 kilonewtons in tension and shear capacity of 64 kilonewtons. So this is just simply working down through each formula, area times strength, and then just working with your units as well to get it back to kilonewtons, and then divide by your partial factor to get 111 kilonewtons. So you're asking here now that 7.5 ton will actually give you 11.1 ton in tension. You're kind of asking then, is the lifting ton, the 7.5 lifting pin, over designed? Not really, because we'll just work down through a few examples. So similarly with the shear, that you work down through it and you get a capacity of 64 kilonewtons or 6.4 ton in shear. So the numbers don't really make any sense right now. We're dealing with 7.5 ton, but you're telling me it's 11.1 in tension and 6.4 in shear. So you're telling me, what can I use? And it's a little bit confusing, but it does work out, and I'll tell you the moral of the story after this slide. So if we have, if we bring these capacity values forward and apply them to a typical lifting scenario. So we've got a 7.5 ton rated lifting pin in a traditional sense, which has approximately 11.1 ton tension capacity and 6.4 ton shear capacity. Note that these are only for the steel failure modes, and the concrete failure modes will still need to be checked. So if we have a slab that is vertically lifted, this diagram here, and that the load on the lifter is equal to the rated capacity. So let's say we've maxed it out. So we're applying 7.5 ton to each lifter, which is less than the calculated capacity of 11.1 ton. So we're happy, vertical lift, the brochure tabulated capacity is fine. If in terms of shear demand, so we'll look at this one here. So this is probably one of the most common cases, is when the chains are angled at 30 degrees. So from the previous module, we can determine that if the tension demand is 7.5 ton, from trigonometry, you can work out that the shear demand then becomes 4.3 ton. So both of these are less than the calculated capacities. 7.5 ton is less than 11.1, and 4.3 is less than 6.4. But when you have both tension and shear acting at the same time, there's an interaction between them. And I won't go through those formulas yet, but when you do work through them, you will find that the interaction check. So you take the relationship between the demanding capacity and tension, and demand and capacity in shear. And for steel, you square your results, and you get a value closer to fully utilized than you do with the individual cases. So this is one of the reasons why the rated 7.5 ton actually gives you higher in tension, because it's not always tension that you're dealing with. You're dealing with combinations of tension and shear on its own. And then finally, when we look at an example of shear on its own, when carrying out the tilting operations, the lifting pin will be loaded 100% in shear. And the traditional approach for tilting was to either double demand or halve the capacity. If we have the rated capacity, we get 3.75, and then the calculated design shear capacity is 6.4 ton, so that's okay. And when we're tilting, you work it out with statics. Traditional method is all, and that's why you end up with I suppose half the capacity in shear. So in terms of this, so what we can say from this example is that in terms of the steel failure modes, it's generally satisfactory to limit the demand to the rated capacity of the lifting pin in the brochures. So once you don't exceed the rated capacity of the lifting pin, that's all the steel checks satisfy. So it's kind of a shortcut. The lifting brochures are generally based on the old global factor safety approach, but from these last couple of slides, we've kind of shown that the Eurocode approach is still satisfied by the brochure rated values. Different products might yield different results, so you have this kind of approach that you can kind of carry out if anyone's bringing a new product to the market or anything like that. You can kind of verify what checks are carried out in the steel. So the main focus needs to be put into the concrete failure modes. There's a lot more variability because you're going to use a 7.5 ton pin a lot for many different types of units, but it's the different types of units that might pinch you because of edge distances, weights, etc. So the pins are generally going to be the same, but the type of unit that you use the pin in is going to be different. So we're going to move on to the tension failure modes for the rest of the lecture. And we've got concrete cone failure, concrete pull-out failure, concrete blowout failure, and concrete splitting failure. And we're going to first talk about concrete cone failure. This is where it starts to get a little bit heavy, but I'm going to go through it without too much focus on these right-hand formulas. These right-hand formulas are pulled directly from the code, but it's the diagrams which the code lacks that would be more beneficial to help understand what factors need to be used where and when. So quickly looking at the formulas, starting at the top, we have a design capacity as a function of the characteristic capacity on top divided by the partial factors on the bottom. So this is just an expansion of the general formula that we had at the start. So we've got all these factors here based on different edge distance scenarios, etc. The next formula is the one for the characteristic capacity, which is a function of the cube strength, the embedment, and the effective depth. So all these factors, such as this Kn factor, they're all available in the code. Recommended here is 11.9. And then we've got all these additional factors, which when you look at the components that are in there, they're just all different functions of C, which is generally edge distance, H, which is generally effective height. So ease and eccentricity, generally don't have to worry about that one too much for a single lifter. But you can see here, particularly when we talk about the edge distances, how much the cone failure shortens for when you're close to the edge. And particularly when you get close to a corner, it's going to be a lot more reduced. So I have nice diagrams here. So for concrete cone failure, when you're working out the area ratio, this A guy here, so you want to first work out what the value is when there is no edge distance, which is AC naught. So it's just, you assume that you have full concrete all around the outside, and this C dimension is a function of the effective height. So it's 1.5 times the embedment, basically, according to the code. So you work that out, and you get your A naught value. But then as you get close to the edge, you calculate your A value, and you get the ratio between the two. And that is basically a reduction factor. It's one of the most significant reduction factors that you will encounter with this. So as if, for example, your lifter was embedded 200 millimeters, it means C needs to be 300 millimeters in order not to have a reduction. But sometimes that's not always the case. You just have to work through the reduction and see what you're left with. So that you can see that's full area. This is about 3/4. When you go to the next page, if you're in a corner, you now have 2 edges to contend with. If you're in a wall panel, you've got 3 edges to contend with. And if you're on the top of a column, you can often have 4 edges to contend with. And you can see then quickly how much your capacity is affected by those scenarios. Quick explanation on the other 3 factors here. Don't really need to go into too much in the theory about this, but again, when you are close to edges and when you have certain effective depths, your concrete is a material that doesn't behave linearly. In the codes and simplifications, it's treated linearly in some situations just for simplification. But when we get to lift and design, there are some subtle changes that need to be applied to ensure that the linear solution still makes sense. And you can see that. So when we are close to an edge, the stresses are slightly different. So the concrete cone failure can't fully develop as normal. So the crack lines will change. That's a factor for that. When we get close to the top surface, so if we have a small embedment, typically less than 100 millimeters, again, the concrete can spall, and if you have too much reinforcement in there, it can actually be a negative, because again, the concrete can't develop its full cone because of the disruption from that reinforcement. And then an eccentricity factor, this usually comes into account. So these formulas are coming from 192-4, which is a general concrete fastening code. So if you were casting in plates with shear studs on the back of it, when you have a group of plates, etc., there's this needs to be taken into account. But for lifting, this is generally taken as 1. And that's kind of the long and short of concrete cone failure. So there's a bit in it, as I said, but the idea is to just help you explain what factors need to be taken into account. And the precursor to any lifting design is always a good diagram. Once you know where your lifting pins are, you can calculate your edge distances, and you can just pump them into the formula. Because as complex as the formulas are, it really is just edge distances, effective depths, concrete strengths, and all different combinations of those. So once you have those few key inputs, you can work down through these formulas. And with the number of formulas that we're going to deal with here, it's very suited to setting up a nice clear spreadsheet for checking these failure modes. The next failure mode then is concrete pull-out failure. So while possible, it really rarely governs. It does not form part of the precast lifting code 15728, but it does form part of the wider Euro code 192-4 on casting in concrete. So I've included it here, so it's just one slide. Generally, due to the shape of the foot, as we spoke about before, of the lifting pin, the stresses propagate outwards into the unit, and the result is a concrete cone failure as opposed to a vertical cylinder, which is bond failure. But dealing with precast concrete, dealing with concrete in general, you may have different applications for bond failure. And bond failure we will talk about a bit more detail in lecture 4 when we're talking about wire strand lifters. So where there's essentially no head on the end of the lifter, and it's just it's reliant on the anchorage of the wire rope or rebar into the concrete. So we'll revisit this later in the course. The capacity calculation is relatively straightforward, simple formula, and it's a function of the load bearing area of the foot. So this is, I suppose, to be a little bit specific, this is like a bolt head cast in. So there's some lifters that have like a bolt head where the forces are almost, the bearing is almost vertical. With the pin head, it's at a slope, and then therefore the forces propagate out at an angle. So bolt head might experience this type of failure. But basically, yeah, it's working out the cylinder and the shear strength of that cylinder using this formula. K2 factor in the code, area of the head, and the concrete strength, and your partial factors. Simple formula, and that's it. So cracked concrete, uncracked concrete, gives it two options in the code. There's a little bit of a discrepancy between the two codes, 15728 and 192-4. What you will notice is that in the 192-4, the UR code will always give two values. It'll give a value for cracked concrete and it'll give a value for uncracked concrete. Whereas in the precast lifting code 15728, it'll give a single value and it'll generally be somewhere between these two. So I think it could be 8.7 for pullout. Maybe, I'm not too sure. But yeah, so the rule of thumb is always use the precast lifting code as your first port of call, and then for anything that you cannot find in the precast lifting code is then to revert back to the general fastening and concrete code. Concrete blowout failure will be the next one. As mentioned at the start, this failure governs in narrow panels where a long lifter is used, but the lifter is close to the edge of the panel, so like wall panels, etc. Similar breakout to the concrete cone failure can be observed, except that this time it's on the side of the unit as opposed to the top of the unit. And there's a high concentration of force at the foot, and then therefore, with very little concrete to the edge, you'll have this kind of pop-off failure. Generally, it'll be more circular, but for the purposes of design formulas, it's simplified into a square for calculating areas and edge distances, etc. The format of the resistance formulas is also similar to what we've seen before, given the critical dimension being the C, how close you are to C1 factor, how close you are to the edge, defines how much concrete could break out, and then you work out, like with the concrete cone failure, you work out your formula for where no edge distances are an issue, and then you work out then the different scenarios if you are close to an edge. Again, we've got some factors here, which comes from EN 182-4. Yeah, your formula is the same here, characteristic capacity, A value. So it gets quite repetitive. You just need to know what geometry and what depths to put in. We have a couple of diagrams here now on the different possible scenarios that you might deal with in terms of blowout failure. So this particular one is where you're close to an edge. You could also have two lifters close to each other. So what you do in that scenario, I have the pen here, you split the difference between them. So you divide S2 in half. So this now is the area that you can account for that lifter. So you're bounded by half the spacing and you're bounded by the edge. So when you're dealing, say, with, sometimes you might have bridge beams, etc., and they could be 500-800 wide. So you might try and fit two lifters in at each end. But you got to realize that when you do put in extra lifters, each lifter is kind of affected by each other in terms of the amount of concrete that they can engage for their resistance. And then if our lifter is quite deep compared to the actual depth of the unit, well, then you're confined by the bottom edge. So in this scenario, we're going to be confined here like this. So half the spacing confined by the bottom edge. So you can see here that, you know, we no longer have this bit of cone to avail of. That's all gone. So we have a reduction on our capacity. Sometimes difficult to reinforce against, so you just have to design against it. Because generally, if your seated dimension is 100 mil, you're not really going to be able to get sufficient steel in around the links, and there's more going to be the cover concrete that pops off, which again is considered a failure. We've got a similar set of values, additional values for the disturbance stresses. But when you, again, not going to go through these in any great detail, when you look at these, it's C for edge distance, S for spacing. N here's the number of factors, but again, in lifting design, we generally deal with one lifter in isolation, so that goes to 1. Your eccentricity again goes to 1. So from the general formulas, a lot of these reduce down quite quickly. The last failure mode then is splitting failure. So as seen on the diagrams, this type of failure can result in horizontal or vertical cracking, depending on the type of unit and lifter position. So like I said towards the start of this lecture, in tension, you're generally going to have a horizontal failure line. So like a wall panel, when you're lifting from the top of the wall panel, you might have a horizontal failure line. In a flat slab, you might have a vertical failure line at the bottom. And this is particularly the case if you were in a corner where you could have kind of a failure out that way and out that way, and the corner breaks off. And then if the corner breaks off, the lifter is loose and the whole thing fails. But there's very simple formulas to design for this. And this is just a snippet from the code. And generally, once you have some bit of reinforcement in there, your design is satisfied. Because we're casting in lifters, we're casting in something, and we can generally avail of this factor down here, which reduces our required area of steel for the reinforcement. If you were post fixing in expansion anchors, you have to double the amount of reinforcement. So there's a factor of 4 in the difference between the type of anchor you're using. So it pays to have good quality control, so you don't have to post fix on site. So simple formula is this K4 factor, your tension force divided by your design steel resistance of the rebar, and that'll give you the amount of steel required. So on the next slide, I have a quick example. So quote anyone's brochure, typically you're going to have a max pin of 32 ton. If you were to say that you have a force in tension in a 32 ton lifting pin of 32 ton, so you have maxed out the lifting pin. If you pump that into this formula here, so where's my little guy gone here? So into this formula here, so we have the 0.5 factor because it's cast in, it's bonded, it's headed. It's a headed lifting pin. 32 ton is 320 kilonewtons times 10 to the 3 to bring it to newtons. And typically reinforcing steel is characteristic strength of 500 megapascals, and divide by 1.15 for your partial factor. So it gives you an area of steel of 3.68 millimeters squared. And if you break that down to what it would look like, so for that type of lifting pin, let's say it's in a wall panel. So I'll just do a little quick sketch here on the side. If I can get that. Doesn't seem to be behaving. don't seem to be able to bring back up to, oh, there we go. Pin, there we go. So if we have a wall panel with the lifting pin like that, tension force 320 kilonewtons, we need 368 millimeters squared. If we think about this in 3 dimensions, you're generally going to have links at the top of your wall panel like that, traveling into the page, and you're going to have lacer bars at the top. So if, say, for example, we just take account of the first link either side of the lifting pin, that gives us 4 legs of steel. So if you divide your 368 by 4, you're going to be left with a value less than 100 millimeters squared. So something like 4 B12s. If your links were B12s, that's all you'd need to ensure that the splitting failure doesn't occur. So that particular failure mode is quite easy to resist, and it's quite compatible with the steel that you're already going to have in your precast unit for your permanent works design.